So thank you for joining me to watch the chapter 1.2, some important crystal structures on our course in solid state physics. So we have 3 sub-chapters in our book that are describing very simple crystalline structures, so cubic structures, and we will be covering the very basics, rudimentary basics of these structures. So we will show you a simple cubic SC structure, body-centered cubic and face-centered cubic structures. I'm hopeful that you are already familiar with these structures, and that's why we can just keep our treatment quite rudimentary. And then we will say about closest packed structures, so basically hexagonal closest packing, HCP, and mention that there's 2 different stacking ways that we can have when we are forming these kind of structures. So we may have AB, AB, AB type A packing, and then we may have ABC, ABC type packing. And we will introduce the coordination number in relation, because that's a useful quantity when we are trying to understand the bonding processes in solids. And then finally in the chapter 1.2.3, we will mention that the covalently bonded solids, most of them will be forming in a diamond cubic structure, and we will introduce about that. So especially when we are looking on the periodic table, the group 14 elements, diamond structure is a very important structure to know how it is, how it looks like, and what are its implications to the properties of the materials. So these are the things that we will be covering in this lecture, and I will now start the actual treatment. So I will first provide you a very general and generic introduction, motivation for this chapter that we will go through the kind of most commonly encountered crystalline structures. And the why we go these is that the cubic structures are also graphically quite easy to understand, so that this is a good way to kind of verify that we understand what we're dealing with here. And after this, in the second chapter, we dive into the different bonding types. And I want to remind you here that it's also good to appreciate that what are the physical microscopic properties and the principles that then keep these structures stable. So that's maybe good to keep in mind. So whenever we have a given structure, there must be something on the microscopic picture that makes this specific structure stable. So that must be there present. But more of that in our second chapter, which is then focusing on the bonding of solids, the different solid types, different bonding types that give rise to different structures. And like I mentioned, conceptually, these cubic structures are the simplest that we can imagine. And in the figure, we are describing the structures that we will be covering next. And later, we will go into these non-cubic structures. So the simplest of those is the hexagonal closest packing type. So in the A, we have a simple cubic. We only have lattice points in the edges, the corners of the cube. In the B, we have a body-centered. And for the sake of clarity, I have highlighted this center center lattice point in blue. But of course, yet we are not describing what is the basis of the lattice. So in reality, we should also just use identical notation here. We're just dealing with the lattice points here when we are dealing with these lattices. So please don't make the error of thinking that somehow we could have different atoms in these locations. They are identical lattice points in a Brava lattice. And then we have in the C figure, we have the face-centered cubic, where we, instead of having a lattice point in the center of the cube, we actually have 6. Yes, can I count 1, 2, 3? Yes, 6 points and additional lattice points in the edges of the faces of the cube. So this is what we then have in these kind of lattices. And some of you, the brightest ones, already think that is this in contradiction to the statement of the earlier lecture that we only have a single lattice point per a primitive cell? No, there's no contradiction, but there's just a point that these cubic structures that we are describing here for the body-centered and for the face-centered cubic, these are not primitive lattices. These are not primitive cells we would be using to describe them. So the primitive cells of these lattice types should actually be something more complicated than just a simple cube. Because and that can be easily appreciated by just trying to count how many lattice points we have per each of those cells. And when we realize that we have actually more than a single lattice point, we realize that this cannot be the primitive cell, since the primitive cell was built in such a way that we only have a single lattice point inside. So that's my brief motivation on the upcoming lecture. Let's now go through the different cubic structures in more detail. So the simplest one we can imagine is a simple cubic structure abbreviated with SC, and that's been shown in here similar to the previous figure. It's not very common when we are actually forming solids, but it's a very simple case, so it's a good starting point because of that. And why it's not very common is that it's a very open structure, so that it's not very dense, and metals prefer dense packing. And if we would look elementary solids, which is a term that means that we are looking at a solid that is being formed by a single piece of an element, and a single element, and from the periodic table, and not, for example, it's not a compound. When we look at elementary metals or elementary solids, most of them are metals. Since the metallic bonding prefers dense packing, this kind of structure is not very favorable energetically. So this is the trouble that we have if you would want to form a solid based on this simple cubic structure. If you would have covalent solids, they are principally okay, compatible with a simple cubic structure, but atoms preferring 6 bonds are not very common, and that's the reason in practice why we don't have these. So more of this in our upcoming chapter on bonding of solids, but I think we can already appreciate here that they depending on what we actually put in here into the lattice points, they might prefer to form given kind of bonds with their adjacent atoms. And then depending on the valence structure, valence electrons, number of valence electrons we have for the specific atoms, we may not be able to have a case where the atom would actually like to have 6 bonds surrounding it. So that's the kind of the downside of this simple cubic structure. And the other lattices that we described, cubic structures, was the body-centered cubic BCC. And please note that the blue in the center is only chosen to clarify that it's inside the center and not at the edges. But there's nothing different between these different lattice points. They are identical lattice points in the lattice. And then the second most simple case is the face-centered cubic. And this is the densest of cubic structures, and that's why quite a bit of the elements that we have on the periodic table form in this FCC configuration. So BCC and FCC are quite common structures. For example, 17 of the elements that we have on the periodic table form BCC lattices, and when they're forming elemental solids. 24 of the elements form FCC lattices, so actually they are quite common. And only the SC structure, the cube, is also the primitive unit cell, and this is something that might surprise you, but I recommend you to consider the definition or kind of defining characteristic of a primitive cell, and it was that we only have a single lattice point inside the unit cell. And here for the BCC and FCC, we see that we actually start having more lattice points than just a single lattice point. For BCC and FCC, the unit cell is cubic, but it's not a primitive unit cell. That's the thing. And in practice, this means that when we would be drawing the generating vectors, AIs, they would not point along the cube's edges anymore. So the parallelepiped that will be formed or would be formed and could be used as our primitive cell, it's not a single cube anymore. So that's the complication that we have. And somehow human mind doesn't seem to be very compatible with more complicated structures, geometrical 3-dimensional structures. So I think that's when we often start having some kind of trouble in understanding what's happening. But hopefully most of the things that we can cover, we don't need to go into too complicated shapes. It's a course, and it's an introductory course. So while I of course try my best to choose the simplest possible scenarios to show what happens, so that I try my best to avoid complicated three-dimensional cases and the kind of most general cases. I will just outline the basics, the basic physical processes that take place and are important, and I will leave you the rest of the generalization to 3D volumes and more complicated 3D volumes for the future studies and future work. And I will show here an example case of a cubic structure, so sodium chloride. And why I chose sodium chloride, and this is the crystalline structure of sodium chloride, is that first of all, we all use sodium chloride daily because food tastes better with salt. And maybe biologically the reason why we like the taste of salt is that all life on Earth depends on it, and all biological organisms must have an adequate amount of sodium chloride on our systems. So that's what we must have. And somehow I'm intrigued nowadays, of older age, that of biology and chemistry and all these other things, that it's a rich world that we have, and somehow sodium chloride to me is a nice example of this kind of richness that we have. For example, why all life on Earth depends on sodium chloride seems to be originating from the fact that we all come from the primordial sea, and we all are organisms that have been evolved from sea creatures. So that's where life began, and since it began from there, how things got involved was that they all life kind of stuck up in needing sodium chloride as a material. So chloride is something that we are using in our processes in cells. So I think it's interesting. Solid state physics is cool. Life is cool. Universe is mind-boggling, and physics is a neat branch of natural sciences. Chemistry too. So let's now go to the hexagonal structures. So closed packed structures are next on the pipeline. And what we have here, generally speaking, metals prefer close packing. That helps in kind of ending up in a case where it's energetically favorable to form a solid. So that's the reasoning why metals prefer close packing structures. And the hexagonal structures are the ones that provide the closest packing of spheres that can be imagined. And that I'm highlighting here in the figure from our booklets, that I'm drawing the spheres. And if I want to minimize the space between the spheres, I can put them on a hexagonal structure. And interestingly enough, there are actually two ways of stacking hexagonal stacks when we start going along the third dimension. So there's the first scenario that we have this AB stacking, and there we have the third layer again resembling the first layer. So that's being highlighted in this figure here, so that we have the first layer, we put in the second layer, and again the blue color has been chosen just to kind of clarify that this is the second layer, but the lattice point is exactly the same kind of lattice point that we're dealing with here on the underneath layer. And then when we put a third layer exactly on top of the first layer, then we have the AB stacking. So that the kind of repeating unit only requires two planes, A layer and a B layer. And this is somehow different, so that one can also place the third layer differently, and that's what then gives rise to a different structure. But when we have this AB stacking, this is exactly the hexagonal closest packing structure, so HCP. But like I already mentioned, spoiled the fun, we can also have a little bit more complicated stacking. So we can have ABC types stacking, where the third layer C is not in an identical position to the first layer A. And that in fact actually gives me a face-centered cubic structure. So this is then shown here. So I put in the third layer, and it's not on top of these points in here. Maybe we can see it better here, that we have the first layer atom here, and then we put the third layer, and it's not actually on top of this. And certainly we can appreciate the difference between these figures, that okay, this is the HCP structure and this is the FCC structure, that there's actually a difference. So this is what happens when we are dealing with these different types of hexagonal structures. So the HCP is a very common structure, and it's very common because it's very common when we are looking at elemental solids. So solids formed by just using a single element from the periodic table. So most of them really are metallic when we are looking at elemental solids. There's just a few covalent structures, ones that form giant covalent structures like a diamond, but most of them are really metals. It's really surprising when you look at the table. So 36 of the elements are forming in HCP. And putting these numbers together, it really seems that most of the table of elements, when we are looking at the elemental solids, is now covered with the BCC, FCC, and HCP structures. So it's quite common, these structures that we have shown here, even though these are the simplest we can imagine. But needless to say that when we go to compounds, the structures may become more slightly complicated. And further concepts I would like for you to keep in mind and appreciate is that there's a thing known as a coordination number. Depending on the kind of branch of physics, are you more like a biologist or chemist working with proteins and molecules, or are you a solid-state physicist? But in any case, our definition for coordination number is that it's the number of nearest neighbors that we have in our lattice. So basically for the FCC and HCP, these maximize the coordination number of these structures, and for them it's 12. And this is one way of telling to us that the coordination number may affect the bonding types and bonding processes. So it kind of tells us already how many neighboring neighbors we have, and sometimes we can directly see that the certain structures are favorable. For example, the FCC and HCP are favorable over the simple cubic SC because the coordination number is higher. So that kind of rules of thumb can be understood by based on these kind of concepts. And then I will say, before moving onwards, that the bonding of solids that we will be covering in the next bigger chapter, it's not a simple process. It's actually super complicated, I would say. And it took me a while to start grasping the kind of the general rules of thumb, that where they originate. So there's a lot of things that we're covering here. Many forces play a role, and especially in transition metals, the quantum mechanics that is being involved and plays a role in formation of the solids, it's very important. So basically the quantum mechanics related to the electron orbitals start being important. And this is actually not very trivial things to grasp, but nevertheless, if you want to understand solids, then we must go eventually there. But next chapter, we will really deal more regarding bonding of solids. And here's an example of one very familiar structure. So we may, for example, imagine that we have water ice. So we have water molecules. That's what I'm graphically picturing there. And then they can, when we go to low enough temperatures, the water can freeze and form a solid. And this solid will have a crystalline structure, a little bit of, although it's polycrystalline, but nevertheless, in small enough scale, it looks like a crystalline. And there's some forces that give rise to the periodicity of the structure. Why water ice does have a periodicity is partly crystal and not amorphous. And this difference must arise from some forces. And those will be covered more in the next chapter. And then I'm showing there you a diamond structure on the left-hand side, or maybe I should say that this is a zinc plane structure, because I'm now having these blue atoms or blue lattice points and radial lattice points here. So this is another case of a structure where the bonding processes and types are very important. But more of this later, like why we seem to have this kind of tetrahedral configuration here. And finally, I will go to the final part of this lecture. So we will speak a little bit of covalently bonded solids. And there I will start saying that what happens when a covalent solid is being formed is that we do have the valence electrons of our elements, and they are being shared between the neighboring atoms. And this is the process that then minimizes the overall energy of the system. And that's the kind of mechanism that gives rise to formation of a solid. Energy is being minimized, so it's favorable for many atoms to actually form a solid and not be remaining in a kind of like individual states. And here in these processes, because we do have valence electrons, it's actually the bond lengths and that are being like the bond lengths in the bonds that are being formed between neighboring atoms, and the directionalities that are more important than just the packing density. So when a covalent structure is being formed, like it doesn't minimize the kind of space between lattice points. It's not the densest of structure, but it really helps out in arranging the bonds in a nice way, so that the kind of energy of the system is being minimized. So that's what happens in covalent solids. And for example, the simplest of examples I can imagine are the different allotropes of carbon. So for example, graphene, and that got its Nobel Prize in 2010, if I recall the year right, discovery of graphene, a single graphite layer. And then carbon nanotubes, that's another example of a allotrope of a carbon. So we take a single piece of graphene and conceptually we just make a roll, a cylinder out of a single graphene layer, and we get a carbon nanotube. Then we may have a graphite, which is essentially many graphene layers stacked on top of each other. And then we have the diamond structure, and this will be covered quite a bit in our course. And then we have fullerenes, nanoribbons, and all not. I think there's hundreds of carbon allotropes out there that have been seen, so that there's actually like a huge amount of different structures. But these ones listed here are by far the most common. And here I have a background in laser physics and optics, so I would just want to point out that there's, for example, connections to laser physics. So very quickly, when we are dealing with actual materials such as graphene and carbon nanotubes and diamond, then we start speaking of branches of physics that also have some direct applications. So for example, like we will soon later discover that diamond is like the kind of best thermal conductor there is. And if you want to make high power lasers, at some point we just need to pump the laser crystals or the lasing media very strongly. And that means that it will absorb light. And when something is being absorbed, that means also that the temperature of the system rises. And then we start, when we are making devices, when we are making high power lasers, we need to cool down the laser devices actively. And in order to effectively cool down something, we need very good thermal conductors. And their diamond is like the best material that we can imagine. It's not the cheapest, it's not the easiest to fabricate and place, but it is the best. Another examples like graphene and carbon nanotubes, they could also be used to make special mirrors, saturable absorbing mirrors, and they could be used to make pulsed lasers. But I just wanted to point out to you that our scope in solid state physics and in this course is not to go towards applications, but it's always there, the applications, and the kind of fact that we can apply solid state physics into other branches of science. It's always there, very near, and if you would just think about it or be knowledgeable enough, we would see that what we learned during this course it's extremely useful in terms of other branches of science and applications. And these actual materials are very prime examples of that. But many of these will be discussed later, don't worry. Hopefully we will also start more appreciating the fact that the importance of solid state physics. So, diamond structure that is associated with carbon. It's not a unique structure, so also other elements form in this kind of diamond structure, or diamond cubic, sometimes said. So especially it's found in group 14 elements, and they form semiconductors. So silicon is a prime example. So maybe you have heard of silicon industry, semiconductor industry. Germanium, GE, is another example of a semiconductor slightly below in the elementary table of silicon, and that is also used a lot in semiconductor industry. We can also form silicon germanium alloys, so CG alloys, and they also are having the same diamond cubic structure. Another example, and again, we're still in the same group 14 of elements, so we may have silicon carbide. It's a very hard material, so the mechanical properties are also good. It's being used quite a lot in industry in different applications, and SiC also has a diamond structure. And interestingly enough, all of these elements, they come from the group 14, so that maybe you start appreciating the importance of number of valence electrons. That when it's around 4 or 3 or 5, then the odds are that the structures that will be formed are diamond-like structures. So that the kind of the bond lengths and directionalities are actually very important. Another example of a material is gallium arsenide, a very important semiconductor, a 3-5 semiconductor, so that the gallium is actually not from the group 14 anymore, but the one from between, the adjacent group, and then arsenide also from another directions is adjacent, so group 15. And then we get yet another semiconductor, a group 5 semiconductor, and this is also forming diamond structures. But the terminology here differs, that we don't say that gallium arsenide and silicon carbide are forming a diamond structure anymore, but we rather say that it's forming a zinc blende structure, because we will actually have two different elements that are forming the compound. But here we get along quite nicely when we are just equating that these are forming diamond structures. But there's more sophistication in terminology. And indium phosphide, that's yet another quite important semiconductor, and that's also forming structures, solids in this kind of three-dimensional periodic structure. So this is what we call a diamond lattice, and here these blue dots, they are to highlight that they are not on the kind of normal location of the lattice. But rather we should think that we actually have a basis of lattice where we have, for example, 2 carbon atoms, and this second carbon atom is slightly misplaced from the lattice point. But what happens here, if you recall the carbon, we recall that it has 4 valence electrons, and these 4 valence electrons would like to form bonds in nearby directions. Here we actually see that we have this kind of tetrahedral configuration, that a single carbon atom or the other elements from the group 14, they like to form bonds in these different 4 directions. And that this is the reason, this directionality of these bonds, that then gives rise to this diamond structure. In some cases, these different atoms, they may be identical, such as in the case of diamond, when we have a carbon atom here. In the case of silicon, we have also just a silicon atoms here, or germanium. But when we have silicon carbide, gallium arsenide, indium phosphide, and others, then we actually have a zinc blende structure. so that we have a different, we may have, for example, a silicon here and a carbon here, or a gallium arsenide here, a gallium here and arsenide here, and then those kind of heterogeneous diamond structures or bipartite diamond structures are called zinc blende structures. So this is what I wanted to cover during this lecture. So we have very briefly went through the most common periodic structures, so the cubic structures and the hexagonal structure, and then we have also talked about the diamond structure. And this is hopefully a good kind of recap for you, because you probably already have covered them in your earlier studies. For example, in structure of matter, we already covered these in quite a bit of detail. So thanks for following me, and please join me in the upcoming lecture, where we are then starting to go to the developing mathematical framework to understand how we could characterize these structures experimentally. So basically we will be then discussing X-ray diffraction. Thanks and bye-bye.